Have you ever imagined that a single particle could take two paths at the same time? In the world we live in, this seems impossible. But in the universe of quantum physics, this is just one of many surprises. When we enter the level of subatomic particles, the rules we know stop working as we expect them to. What seems solid, predictable, and logical begins to transform into something almost magical. Among the most intriguing concepts is quantum superposition, which challenges the idea that something needs to be one thing or another. In this new scenario, a particle can exist in multiple quantum states at the same time, waiting only for an observation to decide its fate. This is one of the reasons why quantum physics is considered one of science's greatest revolutions. And what's most curious, the effects are real, testable, and are already part of the advancement of modern technologies. In this video, we're going to unravel this phenomenon with practical examples, visual metaphors, and a good dose of scientific curiosity. Get ready to see the world with new eyes, or perhaps to realize that the world was never exactly as we imagined it. Let's start from the beginning. At the start of the 20th century, science encountered a curious problem. Atoms, and everything smaller than them, no longer obeyed the laws of traditional physics. Those same laws that explain why an apple falls from a tree, or how a car accelerates, simply failed when applied to the subatomic world. It was at this moment that a new way of thinking emerged, a bold and powerful theory called quantum physics. It arrived as a silent revolution, but soon proved impossible to ignore. This new vision brought concepts that seemed straight out of a movie. The idea of quantum superposition, for example, suggests that a particle can exist in multiple states at the same time. The famous double-slit experiment showed that even a simple electron can behave as both wave and particle at the same time. Reality, as it was thought of before, had to be completely reevaluated. The universe seemed not only stranger than we imagined, but perhaps stranger than we can imagine. And it wasn't just scientists who were intrigued. Philosophers, thinkers, and curious people from around the world began to wonder, if quantum physics is real, what does this say about the very nature of reality? Does reality change when it's observed? What role does consciousness play in all this? Gradually, quantum physics stopped being just a mathematical model. It began to touch on something much deeper, the way we see the world and ourselves. But then, how does this work in practice? Think of a quantum coin. As you can already imagine, it's heads and tails at the same time. Now comes the most intriguing part. What happens when someone observes a quantum coin? At this moment, something almost magical happens. That state of superposition, where it was heads and tails at the same time, disappears. The coin chooses a side and shows itself in a definite way. This phenomenon is called the collapse of the wave function. And this is where one of modern science's biggest discussions comes in. Why and how does this happen? Quantum physics doesn't predict absolute results, only probabilities. In other words, it doesn't tell us with certainty what we're going to see when measuring a system. Only the chance of each result happening. It's as if reality, in its purest form, were governed by possibilities, and only solidified when someone looks. This raises a disturbing question. Does reality exist independently of our observation? Or are we an active part in its emergence? What makes everything even more curious is the role of the observer. And here, we're not just talking about a scientist with a microscope, but about anything capable of making a measurement. A simple detector placed in the path is enough to trigger the collapse. This means that, somehow, observation changes the particle's behavior. What was a delicate dance between possibilities becomes a single concrete, measurable, and definitive reality. But, until when? To better visualize these quantum states, many people turn to something familiar: waves. Imagine the sound of two musical notes playing at the same time. Each note has its own vibration, its specific tone. Now, when these notes combine, they form harmony, or sometimes dissonance. This is exactly how quantum superposition works. Different states overlap, like notes in a chord. And this parallel isn't just beautiful, it's mathematically precise. Superposition would be like hearing both at the same time, creating a unique sound that isn't just the sum, but something new. This musical analogy helps us understand why quantum behaviors are so delicate. Just like in a symphony, Small deviations or noise can change everything. That's why any measurement directly interferes with what the system decides to be. This comparison with musical notes reveals something powerful. The quantum universe is profoundly vibrational. Quantum waves carry information about what the system can be. When they interact, they create complex patterns, like a cosmic melody playing without an audience, until someone decides to listen. And when we listen, the music changes. But before that, it exists in a space where all possible songs are still playing at the same time. This concept becomes even clearer with another example. Imagine throwing, at the same moment, two small stones at different points in a calm lake. The waves that emerge spread out, meet, and then something interesting happens. At some points, the waves add up and become stronger. This is constructive interference. At others, they cancel each other out, known as destructive interference. Now replace the stones with subatomic particles, and the lake with a quantum field. The principle is the same. When two quantum states overlap, they interfere with each other, forming surprising patterns. This quantum interference is one of the clearest proofs that quantum superposition isn't just an abstract idea. It's a real, measurable phenomenon that directly affects particle behavior. Instead of simply choosing between one path or another, the system acts as if all possible paths had been explored. And the probability of the final result depends on how these possibilities interfere with each other. It's a dance between the possible and the observed. But pay attention. This interference only happens while the system remains untouched. That is, before any observation or measurement. Just trying to peek at what's happening makes the magic disappear. The interference pattern vanishes, and the particle behaves as if it had never been in superposition. This phenomenon, repeated in various interference experiments, is one of the most intriguing demonstrations of reality's quantum nature. And this leads us to the most famous experiment of all. The double-slit experiment is a physics classic and perhaps one of the most bewildering of all. Imagine a barrier with two slits, and right behind it, a screen capable of recording impacts. If we launch classical particles like marbles, they pass through one of the slits and form two well-defined groups on the screen. Now, if instead we use a wave, like light or sound, the result is quite different. A pattern of stripes appears, resulting from interference between the waves that pass through both slits. Here comes the part that defies all logic. When we use electrons, sent one at a time. Even so, over time, the pattern that appears on the screen is the same as a wave, with interference fringes. This indicates that each electron interfered with itself. But how is this possible? This can only happen if the electron passed through both slits at the same time, like a wave in superposition of paths. Quantum physics predicts exactly this, and experiments confirm it. But the best, or worst, is yet to come. If we place a detector to observe which slit the electron passed through, the interference pattern disappears. From the moment there's a measurement, the behavior changes. Now it acts as if it had chosen only one slit. This reveals something profound. The simple act of observing alters the experiment's outcome, and forces us to rethink what a particle is, what a wave is, and what is, in fact, real. But is all this just theory? At this point, perhaps the doubt still remains. Is quantum superposition just a mathematical tool? A kind of trick to predict probabilities? The short answer is no. Superposition is real, measurable, and has been confirmed in various experiments. When we see quantum interference patterns, we're not dealing with abstract theories. We're facing a physical phenomenon that only exists if quantum states really coexist before observation. A good example of this is the use of superposition in modern technologies, like quantum computers. These devices work because qubits can exist in multiple states simultaneously. This allows them to perform parallel calculations on a scale that would be impossible for classical computing. If superposition were just a theoretical concept, none of this would work in practice. But it does work, and it's precisely this strangeness of nature that we're learning to explore. Another important point: the possibilities contained in superposition don't remain isolated from each other. They interact, interfere, create new patterns. In other words, superposition is more than a sum of alternatives. It's a state of connection between what could be and what hasn't been decided yet. And this is what makes the dual behavior between particle and wave so fascinating. Quantum reality, it seems, isn't made of certainties, but of intertwined possibilities. This leads us to a natural question. If quantum superposition is so real, why don't we see a chair being in two places at the same time? Or a person drinking coffee and tea at the same time? The answer lies in the quantum scale versus human scale. Quantum effects are incredibly subtle and delicate. They occur at the level of tiny particles, like electrons, and are easily disturbed by any type of interaction with the environment. When something is observed or interacts with the external world, what we call decoherence, it loses its quantum behavior and begins to behave in a classical way. Just adding a detector to the double-slit experiment, for example, makes the dual behavior disappear. What was once a wave in superposition transforms, in the face of measurement, into a common particle with a single path. It's as if the act of looking froze reality into a single possible version. This boundary between the quantum world and ours raises profound questions. How far does the observer's influence go? Is there a clear line between what's quantum and what's classical? Or is everything quantum, but we can only see a small part of it, already collapsed by constant observation? Quantum physics doesn't give us all the answers, and may never give them, but it invites us to face the nature of reality with fewer certainties, and much more scientific curiosity. And this is where we reach the end of this journey. The more we delve into the universe of quantum physics, the more we realize how much it challenges our most basic intuitions. Quantum superposition, with all its mystery, shows us that reality can be much more malleable than it seems at first glance. Instead of definitive answers, we find new questions. And this is exactly what makes this journey so fascinating. The fact that understanding the universe is also understanding our own limits. Perhaps what's most thought-provoking is realizing that, even with all the technology and scientific advances, we still find ourselves facing a wall of mystery. The dual behavior, the role of observation, the collapse of the wave function. All of this is still being debated. And the truth is that the more we learn, the more we realize how much we still have to learn. The quantum world doesn't fit perfectly into our ideas. It demands that we rethink concepts like causality, time, and even what we call existing. So, here's an invitation. Keep exploring. Question, read, watch, try to think differently. After all, this is exactly what led scientists like Einstein, Bohr, and Heisenberg to open doors to this new universe. And who knows? Perhaps the next great discoveries will come from ordinary people, curious, restless, and passionate about understanding how everything works. If you identify with this, subscribe to the channel, activate notifications, and join this community that doesn't accept the obvious as a final answer.